And for that, let's do a simple example of a derivative like x squared or something. And let's look at it from numerical points of views and graphical points of views and stuff. So as an example, let's take a look at y is equal to x squared. And we know that y prime is equal to 2x and then be done with that, right? But if we take a closer look at it from a graphical point of view, and let's actually focus on a particular point. At x is equal to 1, say, what we did, or what we would have done when you first started learning about derivatives, is to find like secant lines or something like that. And then from the secant line, you found like the slope. And so the slope of the line that you might have been looking for would be the difference in the x's, difference in y's, and stuff like that. So delta y, delta x, which is 1 minus 0 and 1 minus 0, which is 1. And what this would give us is it would give us an approximation of the slope of the tangent line, which is the derivative at that point that we're looking for. And so at some point we did some other fancier things where we found the secant line going to another point. And then maybe we took the average of those two to get the actual slope of the tangent line that we had. All right, so my point is that we know a lot of things already when we're looking at y as a function of only one variable x, or in other words, when we have functions going from r to r, we know everything there is to know about derivatives because that's what we studied in Calc 1. Okay? So we can imagine taking limits as well. That's a formal definition of your derivative. So let me just say the formal definition is something like this. It may be a little bit different from different contexts, but a lot of times they use h as your variable that's going to approach 0, and then f of x plus h minus f of x all over h. So this approach takes a look at the secant lines and makes the secant lines, these points, get closer and closer to the point that's in question. And then at that limit, then you would find your derivative. And this is the derivative at a particular point. Oh, I'm sorry, there's mistakes here. This should have been fixed. This should be a. Because if we want to change this to a general f prime of x, then you change your a's into x's. So in general, I'm going to rewrite the whole thing again, except instead of a's, I'll put x's. Then this becomes your derivative function. Okay. So this is like our background. This is our assumed knowledge coming into this class. So when we'll start taking derivatives, we'll start looking at falling back on these ideas. All right, let's take a look at the derivative for our new functions now. Let's start with a two-dimensional rate of change. So now let's say we have this thing. Remember, this is usually called z is equal to f of xy. When we took derivatives before, we said we take the derivative, just take the derivative, and it was clear that you had one independent variable and one dependent variable. So now we have a little bit of an issue here, and our issue is that now we have two independent variables. So finding the derivative with respect to what is the question now. So we could still write d something over d, and now our question is, if we have two variables, how are we going to negotiate this idea of what we want to take the derivative with respect to? Okay, so it turns out that in this case, we will end up with two different derivatives, or as many derivatives as you have independent variables. Now this would be called the partial derivatives. Because these derivatives are with respect to one variable, but then the other variable is not involved, or is involved in a way that you can pretend that it's constant. And then same thing would happen to the other variable. So these are the partial derivatives. And the notation is going to be a little bit different now. Instead of df dx, for example, since we want to distinguish from a partial derivative versus a regular derivative, we're going to change the way we write our d. And we're going to write our d like this. So a little curved with respect to x. Partial derivative of f with respect to x. So an easier notation might be to say you're going to take the derivative of f instead of putting a prime there, because a prime doesn't make sense anymore. A prime tells you to take the derivative with respect to the independent variable. But if you have two independent variables, which one are you going to take the derivative with respect to? So the prime doesn't make sense. Instead, people start to use a subscript. And then they say f sub x to say x is you want to take the derivative with respect to x. So that's just another notation. So although this is an easier notation, a lot of times you see this notation, the Leibniz notation, in many different contexts. So let's be flexible and be able to do both. And by definition, this deals with two variables. So your f has two variables. I have to make room for two slots here, right? And what we're going to do is we're going to assume that y is fixed. So we're going to assume that y is not going to change, and x is the one you're taking the derivative with respect to. So we'll do that x plus h business that we did in the past. And so we're saying we're going to take the derivative with respect to x, but we're going to hold y constant. And if you look at this formula compared to the formula that we saw back in Calc 1, you'll see that it pretty much mirrors that idea that you're taking the derivative with respect to x. X is your variable, and y is just assuming y is a constant. Let's pretend that y is some fixed number. Okay? We can do the same for the other one. Partial of f with respect to y, or f sub y is equal to f of x. And then now the y is the one that's changing with a plus h. So f of x comma y plus h minus f of xy, all of them over h. Oh, I'm sorry, there's a limit there that I forgot to add on. I'm going to squeeze in the limit here. So limit as h approaches 0. All right. Now, we could dig down and really do limits and stuff like that with this, but this is just really a limit of one variable, and the variable is h. And I'm not too concerned about that at the moment. So what I'm interested in doing is looking at this from a numerical point of view, looking at this from a graphical point of view, and then finally doing some simple problems where we're taking derivatives, and then maybe go off and do some higher derivatives after that. So let's take a look at these derivatives from a numerical point of view. And what I thought about from a numerical point of view is I brought up the idea of the Windchill factor last time, but I didn't do anything with it. So now I think maybe we can look for a Windchill factor formula or table and see if we can find derivatives of that. So let me do a quick search. I know this doesn't really apply too much to California. But get a lot of pictures for Windchill factors already, so let's take a look at this one. So here they even give us a formula, an actual symbolic formula down here that the Windchill factor is 35.74 plus something times t plus something times v plus something times t and v with some powers and stuff. But I think in most cases a lot of people find that difficult to work with, a lot of non-STEM people. But you guys are all cool with that, right? Because you guys can understand formulas. So what they do instead is they make a table for regular people to understand. So here's a table of a Windchill factor. What does this mean? That means, let's call this W. No, W is for wind. Let's call it C. C of W, comma, T. So, chill, wind, speed. They call it V here. Maybe we should have just called it V. Let's call it V, sorry. Wind, speed, or velocity, that's why they call it V. And then this is T, temperature. So the actual wind chill factor is dependent on the wind and the current temperature without the wind. So what they're saying, for example, is that if the wind is blowing 20 miles per hour and the temperature is 10 degrees Fahrenheit, then the wind chill factor makes it actually feel like it's 9 degrees below zero. And what they do is they, over in this particular graph, or in this particular table, they color code it so that if you're in this kind of a medium bluish region, you have about 30 minutes before you start getting frostbite. If you're in this purple region, then you have 5 minutes before getting frostbite. So I think all this stuff is really just in the North and South Pole or something. I don't think it ever gets that cold in the middle. But anyways, here's a wind chill factor table, and in our example over here, c of the velocity, the wind speed is 20 miles per hour, blowing 20 miles per hour, and it's actually 10 degrees out, then the wind chill factor is -9. That's what that says. So now the question might be, if at this very moment the wind is blowing 20 miles per hour and the temperature is actually 10 degrees Fahrenheit, what would happen if the wind started to pick up and the wind started to blow 25 miles per hour? So what we're looking for essentially is the derivative, the rate of change of the wind chill if the temperature goes up. So let's ask that question. Let's ask it more formally. Let's say, maybe I should type this up. What is the rate of change of wind chill if the temperature goes up from, and for this I'm just going to refer to this as a point, from 20, 10, assuming that you know that 20, 10 refers to 20 miles per hour. And 10 degrees. How do you make that little dot, degrees? Yeah. So what we could do is we want to find the rate of change, so the partial derivative, since there's two variables here, we're taking the partial derivative of the chill, the wind chill factor, with respect to the change is the temperature going up. It's the rate change of the wind chill with respect to the temperature. Okay? So there's a couple ways to do this, and the best way to do this, or one good way to do this, is to fix your wind assume wind or velocity is constant at 10. Was it 10? 20, at 20. Assume that your wind chill is constant at 20. And what you're going to do is you're going to find the rate of change maybe when the temperature goes from 15 to 10, or the temperature goes from, oh, I want the temperature to go down, sorry. Goes down. I want to kind of go forward like this. I guess it doesn't matter, go up, go down, whatever. Maybe I do want it to go up. I'll just put a negative sign if we need to. All right, so assume the wind velocity is constant, and so what I'm going to want to do is I'm going to want to compare what's happening with the change of wind chill over the change of temperature. So what we want is to find dc dt. We're going to just estimate this. This is approximately equal to the change in the chill divided by the change in temperature. And if I'm looking at the chill factor at -9, there's two directions to go, going up and going down. So what I want to do is I want to take both of those into consideration and just find the average between them. So if I go from -9 to -15, that is a change of temperature from 10 to 5. Does that make sense? Looking at this graph, looking at this table. So the change, and I have to keep the order is important. So -9 minus -15 divided by the temperature of 10 to the temperature of 5. Okay? So what is this? This is 6 over -5, 6 over +5. And what's that in your calculator? That's like 1.1? .2. And it's positive, so maybe this is an up. So here's one set of values. The other set of values can be taken from going from 10 degrees to 15 degrees. That's -9 to -2. So -9 minus -2, and going from 10 degrees to 15 degrees. And this is a -8 over -5. So this is, let me guess, 1.6? 1.4? Yeah. So then the average between them is going to be about 1.3. So it looks like there's a change in temperature, a 1.3 degree change. If it's going down, then we can think about it as a drop. So it's a 1.3 degrees Fahrenheit change. And if the temperature goes up, I guess we can say if it goes down, since I crossed it out and put down. So this is a temperature drop. Oh, that's a wind chill factor drop. So the wind chill, let me say that again. It's a 1.3 degrees Fahrenheit change in wind chill if the temperature drops a degree. Okay. Does that make sense? There's two aspects here. One is understanding the question. Two is doing the work to answer the question. I'm hoping the math part is easy. It's reading the tables, making your slopes, finding those slopes and find the average, and then that's your rate of change. That's your derivative. All right, I want to squeeze this on the same page here, which means we'll have to scroll up and down and take a look at that table again. But as a slight change in the problem, let's say we want to know what the rate of change in wind chill is if the wind picks up. And since we're doing an actual problem here, we have to specify that we're at a particular point. And our particular point here is we're at the point 20, 10, -9. All right? So it's kind of like the same sort of work that we were just doing. We're looking for the partial derivative of the wind chill with respect to the velocity this time, not the temperature. And then, like the other one, we're going to find the rate of change in the wind chill over the rate of change in the velocity. And so again, we're going to come up with a table. We're going to come up with two of these rates of change, one going from there forward, one going from there back, and then find the average. So the change in the wind chill, let's take a look at the change in the wind chill, and we have to go change in velocity. So when we're looking at that change, oh, this is green. All right, match it up with purple. So the green is this work that we're doing, the rate of change in the wind chill over the rate of change in the velocity. So the wind speed over here, the velocity goes up and down. So I want to know about these changes as my wind speed goes up or down. So let's pick the one going up first from 20 to 15. And this is -9, and the wind chill drops to -7 or increases to -7 if the wind drops from 20 to 15. So -9, -7, -9 minus -7, and then the temperature goes from 20, or I'm sorry, from the wind speed goes from 20 to 15. So I have a -2 over +5. Is that a 0.4? -0.4. And then I'd find the same relationship, but this time with the speed goes up from 20 to 25, the wind chill goes from -9 to -11. So -9 minus -11. That's what happens to our wind chill when our speed, the wind speed goes from 20 to 25. So here we have a +2 over 5, -5. So it's -0.4 again, which means average is -0.4. So your wind chill drops -0.4. So as the wind speed increases by 1 mile per hour, because they're mph, right? Wind speed, mph. So as the wind speed increases by 1 mile per hour, the wind chill drops by 0.4. Okay? Does that make sense? So it's based on the table. You find your place in the table because these types of problems will always give you a starting point. So currently at 20, 10, speed is 20 miles per hour, temperature is 10 degrees. Your wind chill is -9 degrees Fahrenheit. So if you're at that point in time, if your temperature goes up, then your wind chill is going to go up. I guess if it goes down, then your wind chill is going to go down by 1.3 degrees. And if your wind speed goes up, your wind chill drops down by -0.4 degrees. Okay? So those are the rates of change. Any questions? Okay. All right, now let's take a look at a more general graphical point of view of these things, and I'm going to insert symbols as we go along too. So we'll take a look at what really happens to the graph as we fix it. We could actually use the same problem because the graph is, the function is given here. But I don't know quite how this function looks like. Oh, we'll graph it someday. All right, for today we'll just use my generic graph. Remember my generic graph? Uh-huh. And as we take a look at the graph, we'll also take a look at the symbols that are involved here. All right. Let's get our surface. And let's label our surface. Z is equal to f of xy. Find a point down on the xy plane. On the xy plane, I can just represent it with a pair of numbers since it's xy plane. But we can also look at it being up on the surface. Now, if it's up on a surface, my point has the same x and y, but it has a z component to it. So what do you think the z component of this is going to be? We could call it c, but it should be something specific to what we have here so far. So it's the function, right? The function describes the height at any point. So if I'm at the point AB, the height of that point is going to be f of AB. You guys okay with this? You can call it C if you want, but I'd rather call it that. What are we going to do again? Oh, partial derivatives. So partial derivatives, what we're going to do is we're going to hold one of the variables fixed. Let's focus on this partial derivative first. Partial of f with respect to x. When we do this, we're going to hold y fixed. In fact, if we're looking at it specifically at this point, y is equal to b, so we can hold y is equal to b as some fixed value. Now my graphing program is kind of cool. If I just type y is equal to b, or an actual number, it's going to draw a graph for me. Y equals b is a graph of something. Do you know what that graph is? A what? It's a plane. Tell me more about this plane. X-axis? XZ plane. So y is equal to b is some b measurement. But when you write this down, or when you try to graph this, or if I say this is a graph of something, this is a graph of a plane that is parallel to the XZ plane. Let's see if we can draw that. I guess I'm more concerned about this. What did I just draw? It's the what? It's the intersection between that plane y is equal to b and that surface that I have. Now let's take a look at this from a two-dimensional point of view. I'm just guessing it kind of looks like this, maybe. Oops, I labeled my axis wrong. So this isn't exactly the YZ plane. This is the plane y is equal to b. But the image that I can get, if I look at it flat directly from the YZ axis, I would get something like this. So I've kind of flattened my view. Instead of looking at this from 3 dimensions, I'm looking at this from 2 dimensions now. And I've flattened my view, but this point that was on the floor is this point here on the floor, so to speak. And this point that was up here on the surface is this point over here on my graph. Now I know y is equal to b. How should I label this point if I want to label this point as a 2-dimensional point? A f of a. Technically, I still need to put b in there. If you want, you can insert that b there, but the y value is equal to b already, so I don't think that's that necessary. And what I do want to do is I do want to take a look at this from a 2-dimensional point of view, because we know everything about 2-dimensional points of views, right? Certainly find that slope of that tangent line right there. And that's what we're looking at. If we want to relate this partial derivative as a slope, it's a slope of the tangent line going in a specific direction, and that specific direction here is going along the x direction where y is fixed. Okay? So because y is fixed, the rate of change here is just going to be the rate of change with respect to x and z. Delta x, delta z, and so that's what you're looking at. So the df dy, we're going to hold x fixed this time. And I'm going to fix the x at x is equal to a. And we can tell the same story here. So instead of just retelling the story, I'll just draw the pictures. We have x is equal to a is a plane parallel to the yz space. And then it's going to have a cross-sectional cut that cuts through that surface, through that point that we saw earlier. So we can draw the same picture when x is equal to a. And then to find the slope of that, we're really just focused on the change in y and then the change in z, or in this case, the change in f over the change in y. So then we have this tangent line. So the derivative is going to be the slope of the tangent line going in that specific direction now. All right? So we will redraw these pictures again tomorrow. So if you can, take a look at it tonight or whenever. See if you can make sense out of these planes and these lines and these graphs and these curves and the points and where they exist, because we're going to do a little bit more on this tomorrow. But for now, I think we can say that we're good with partial derivatives. So this is the geometry of the partial derivatives. Okay? All right, let's do some examples of partial derivatives. And this is the easy part. And I'll try to use different notations every now and then. So let's say you had f of xy is equal to x squared plus y squared. Nothing like an old paraboloid to get us started. We can find df dx by taking the derivative of this with respect to x and pretending that y is a constant. Now, if y is a constant, you can just pretend it's 5 or 7 or something like that. Don't pretend it's 0, because 0 is a special constant. But if you take the derivative of this thing with respect to x, this would be 2x plus a constant. Well, the derivative of a constant is what? 0. So that's gone. So the derivative of this with respect to x is just 2x. Derivative of the function with respect to y is similarly equal to 2y. And then that was a really simple example. Do another one. So this time I'll change the notation a little bit. I'll have z is equal to this thing, and I want to find zx. Partial of z with respect to x. What's this going to be? 2x plus what? 4y. And then this is a constant, so that's done. Zy is equal to 0, 4x minus 3y squared. Okay. Now one of these is wrong. Yeah. No, I think it's right. Does it look right? All right. Let's do one more. So this time I want to find the partial derivative of z with respect to r, and then the partial derivative of z with respect to theta. What's the partial derivative of z with respect to r? 2r. What? Not done yet, am I? Sine theta, cosine theta. It's a constant, right? If you're adding, the constant disappears, but if you're multiplying, it doesn't just disappear. It's all just part of that. All right, how about this one? dz d theta. What? R squared. Do we want to put parentheses around here? It looks like I have a product, right? So I need to product rule. And this r squared is constant, so I can choose to have that distribute, or you just leave it out and then just work with the stuff inside. So it's derivative of the first times the second plus the first times derivative of the second. Yeah. You want to get triggy on me. Now let's not do that. It's just going to get all confusing. So trig formula says that this is equal to cosine 2 theta, but I'm good with this. Questions? All right, well, let's take this a step further, and let's take a look at higher derivatives. And let's do that example over here that we did already. Let's take this example. So in taking this example, if we want to go take higher derivatives, we can take higher derivatives. Now each of these things over here, each of these results in its own, on its own, is a function of x and y. So really, we could take the derivative of this with respect to x and then take the derivative of this with respect to y again. So that kind of makes sense, right? So we can go from here and say, what if we want to take the derivative of zx with respect to x? And that is written as zxx And that is just taking the derivative of this thing with respect to x. What's the derivative of this with respect to x? 2. Similarly, we could take the zx and then take the derivative of this with respect to y, and that is also known as zxy. And what's the derivative of zx with respect to y? 4. Right? All right, let's do the same thing with this. Take derivatives. Let's take the derivative of zy with respect to y or x. This is also known as zyx. And that's equal to 4. Zy, now let's take the derivative of this with respect to y, zyy, and this is equal to negative 6y. Okay. All right, that seems kind of fun.
What's the notation when it's dz?
Oh, yeah. So the zx is the derivative of z with respect to x. And actually, sometimes people write it like this, d dx of z, right? So the operation in Leibniz notation happens on the left side. So if we want to go one derivative higher, derivative with respect to y, so we take our, on this side, we take our zx, and then we apply y to it, we get zxy. That's what we got over here. But on the other side, we have to apply it on the left side, so we apply d dy of dz dx. And remember that d dx, d dy are operators, and z is your other dependent variable. So this, again, if I force this z to move out of there, I get d squared dy dx of z, or d squared z over dy dx. So the basic idea is that if you're using Leibniz notation, you're reading this from right to left. You're taking the derivative with respect to x first, and then with respect to y after. If you're using the subscript notation, you're going from left to right. Take the derivative with respect to x first, and then with respect to y. Okay? No. He was, in fact, a really brilliant man. I don't know if he meant for this to happen when he came up with this notation. Now, we attribute the notation to Leibniz, but it's been used and modified over the years, and so. Okay. The good news is that if we're dealing with nice and continuous functions, I don't know if you noticed this, but these two answers turned out to be the same. It turns out that with nice and continuous functions, which is what we're going to be basically dealing with, we're going to see that these are called mixed partials. So the mixed partial derivatives So if f is, I'll just put nice in quotes, as in continuous, differentiable, and all that. So if it has nice properties, like all polynomials and a lot of the trig and exponential functions, those are all nice. It turns out that the mixed partial derivatives are equal to each other. So the partial, I'll put x and y. xy equals partial of yx. I think there's a name for this. I forgot what the name is, but okay, any questions? All right, I think that's good for today. We got the partial derivatives. You got some geometry behind the partial derivatives. Tomorrow we're going to continue to work on the geometry of the partial derivatives by examining the tangent plane. And with planes, we're going to do vectors and cross products and stuff like that. So prepare.